Welcome back. In this final main video for this week, in week 4, we are going to look at sort of the crowning jewel of what we have been discussing till now. This is known as the Gauss-Newton algorithm. We'll use the short form GNA. And the purpose of this is nonlinear regression. Remember what nonlinear regression does. It is we have a bunch of points and we could have a multi-parameter model which is highly nonlinear in the parameters. Okay, so this kind of behavior you will not get from linear models, and you want to fit it here. So we basically have mathematically y hat equal to some function. Okay, so some function, let's call it h of w, or we call it h of x typically, but with the parameters w, and this h is nonlinear in w. We don't care what it is in x, but we care about what it is in w. So that's what we are trying to solve for ultimately. However, having said that, we want to basically solve the least square problem. Now I'm, instead of calling it j, I'll call it s, which we also use, which is the sum of the residuals of y minus y hat I square. If you wish, you can put a 1 over m here or not. I am not going to put it for now. I equal to 1 to m. This is what we want to minimize. We want to minimize s. That's what the regression problem boils down to. Y hat is given by this curve. Y is given by these points. And we want to minimize the gap between the points and the curve. Okay. So what is the issue? The issue is, as usual, what we discussed before. The issue is this now is nonlinear in W. When it was linear in W, okay, when linear in W, what is linear in W? Y hat. Okay. So if y hat was, if you remember, the matrix was x times w, then we knew how to solve it. Then the solution was, we would write it as x transpose x, w equal to x transpose y. Okay, so this was the solution. Now the question is this, can we do the same trick now? Okay, can we do the same trick now in order to whatever we did in the last video, which is, if we know the solution to the linear, can we now change it into multiple steps of the nonlinear problem as a multiple step of linear problem? So we will try the same trick again. Okay? And we will see if we can derive the Gauss-Newton algorithm now. So the way we are going to do is the same, which is take a guess. As usual, the first step is take a guess for W. Okay, so if you have a nonlinear regression problem, for example, we had the case where we had 1 e to the power minus dx as y hat, then that means take a guess for A, take a guess for B. Okay, so W in that case would be A comma B. Another set of people would call this A. Okay, so I'll use this notation interchangeably within this video. I will both use A as well as W. Depends on what people find more convenient. People like to use A because it's more indicative of these variables A and B. Okay, so take a guess for A, W. Now what will happen is this W will not minimize our S. Okay, so that's kind of obvious. We have taken a random guess for S. Now, what we will do is, now let's say that the new W is equal to W plus some delta W as usual. And what we want to do is, can we create a linear regression problem in delta W? We could not create a linear regression problem in W, but perhaps we could create a linear regression problem in delta W. We'll use the same trick that we did before. So here it is. This is the problem we wish to minimize and see if we can create a linear regression problem there. Okay. So let's try to do that. Please pay careful attention. This can get slightly confusing. That's my experience. So S is sigma. I'm going to switch the signs because it's usually easier to work with y hat I minus yi square. Let's call this Ri. Okay, R stands for residual. You can call it small I R also, which I did earlier, but I'm going to call it capital Ri. Capital R is the vector y1 hat minus y1, y2 hat minus y2. Basically, R is the vector capital Y hat minus y. All right. So now we have R as a vector, which is a function of y and y hat. Now, y hat itself is a function of W. Okay. So here is the trick. So I'm going to say R is sigma R transpose R. This R, which is y hat minus y, can this be linearized in delta W? That is the question. Now we already have R at W, that is our current residual. So we can say R at W plus delta W is going to be R at W plus the same thing that we did last time. If you wish, you can write this as del R del W1 times delta W1 plus del R del W2 times delta W2. You have to be a little bit careful. Similarly, R will have multiple components, and we can use that here to our advantage. What are the multiple components of R? The multiple components of R, you see, this is R1, this is R2, and you will go until how many ever equations are there? This is Rm. So now, this is going to look like, for each row, you will have something like del R1, del W1, del R1, del W2, multiplied by delta W1, delta W2. If I open out this set of equations for every row, then this will look like del R2, del W1, del R2, del W2. You keep on going till del Rm, del W1, del Rm, del W2. In case you have only two W's which are unknowns, or you can call this, for our case, I'm going to make this A and B. So that we can easily apply it to the specific case that we looked at, delta A, delta B. Okay. Same thing. This I am calling delta A. This I am calling delta B. Some people find this notation easier. This as A and this is B. So these are the two parameters. You can think W1, W2 or A1. Now, what does this look like? So this looks like the following. This, of course, is once again the Jacobian matrix. So we can say that R at W plus delta W is R at W, which we know, plus the Jacobian matrix multiplying, let's call this delta A. Delta A. In order to not get confused with what the Jacobian is, let's work this out a little bit further. What is R1? R1 is y hat 1 minus y1. So what is del R1 del A? This is simply del y hat 1 del A, because this part is 0. Similarly, del Rm del A is simply going to be del y hat 1 del y hat m del A. And in general, del R del A will be del Y hat del A. Similarly, del R del B is going to be del Y hat del B. Okay. So we can now put this together and let's call these as Z. Okay. So this is the standard notation that is used. So I'm going to say Z is the matrix del Y1 hat del A, del Y1 hat del B, del Y2 hat del A, del Y2 hat del B, so on and so forth, del Ym hat del A, del Ym hat del B. Okay. Now, just before we move a little bit further, in case some of you are confused, remember for a linear system, okay, so let's say we have a linear system, and in that case, y hat would be, or let's say y1 hat would be a plus b x1, since I'm using a and b. Similarly, y2 hat would be a plus b x2, and then z therefore would be 1, 1, 1, 1, 1, and you would have x1, x2 up till xm, which is exactly the design matrix. Remember that capital matrix X that we used for our normal equations, it sort of gets resurrected here. Okay, so in fact, the most general derivation is the one that we are doing. This works both for linear systems as well as for nonlinear systems. So Gauss-Newton, when you apply to linear systems, would converge in one step, and it will give you exactly the normal equation method. Okay, so this is just to tell you that there is nothing strange. All we are doing is we are differentiating the model with respect to the parameters. It might look strange while we are doing the derivation, but that's exactly what is going on. Okay, so let's go back to this equation. What were we trying to do? We were trying to write the nonlinear regression as a linear regression problem in the changes. So remember now, R of W plus delta W is R at whatever the W is, plus I am now going to call it the Jacobian multiplied by the change. So this is the Jacobian. This is the change in parameters. And this is what we are trying to solve for. Now, what we are saying is S is sigma of Ri square, but Ri is this, and Ri is linear in delta A. I hope you can notice that. Okay, so this term is known. This term is known at the particular W that we have chosen. All the variable there is delta A. So now we actually have a linear regression problem. So another way of writing it is of R at the current W plus Z multiplied by delta A square. We want to find out the minimum with respect to delta A, okay, because that's the only variable that is left. So instead of solving one non-linear regression problem, we first solve, we take a guess, then solve a small linear regression problem, then update the guess, just like what we were doing for our non-linear roots so far. Okay, so it works in exactly the same way as before. This becomes clearer when you see the code. Okay, now we already know how to solve linear regression problems. Okay, so for example, if S1 or S prime was sigma of, in our case, it was Y, or let me write it this way, XW minus Y square, then the solution was x transpose x w equal to x transpose y. Now let's compare apples to apples here. In fact, let's make this minus y and this plus, just so that we don't have to do too many sign changes. So now we can see the correspondences. The correspondences are z has become x, as I just told you. W has become delta A. Okay, this is just like the linear cases that I showed you earlier. And R has become minus y. Okay. So now we can write our equation. So the solution to this is, you can derive it, but it's easier to use our earlier results. Instead of x transpose x, it's going to be z transpose z. Instead of w, it is going to be delta A is equal to x transpose, which is z transpose, multiplied by y. Now we are going to get minus r. Okay. So another way of saying it is z transpose z delta A equal to minus z transpose r. This is called the Gauss-Newton algorithm. The Gauss part comes from using the least square, and the Newton part is because we linearized, just like we do with the previous nonlinear linear systems. So what is the algorithm? The algorithm is like this. For a nonlinear regression problem, so let's say you have y hat is some function of x, but more importantly, the parameters are a1, a2, a3, or w1, w2, w3, whichever way you want it. I will use a because I've been using abc right now. If we want to minimize sigma of yi minus y hat I square, and y hat I depends on these parameters, instead guess. So the first step is guess for a1, a2, which we will call a initially. Then improve guess by solving this equation. Z transpose Z delta A equal to minus Z transpose R, where Z is the Jacobian matrix. To calculate del y hat, del A1, del y hat, del A2, etc., etc. These entire columns for each data point. So for example, del y1, del y1, del y1 hat, del an. And R is simply the residual. Is y hat, y1 hat minus y1, y2 hat minus y2, ym hat minus ym. Some people also call the negative of this as d for the difference. So this would be y1 minus y1 hat, y2 minus y2 hat, and that way you can avoid the minus. So another way to write it is z transpose z delta A equal to z transpose d. Either of these are fine. So this in essence is our Gauss-Newton algorithm. It is messy. I'll confess it's messy in the sense, not in terms of programming, which I will show you. It's actually a very simple program to write. When you calculate it by hand, it is messy. So again, I'm going to recommend that the code that I'm putting up, you at least try a few steps by hand. Okay, typically within IIT, where we teach this course, we do insist that people do solve this equation by hand in all the occurrences of inverse heat transfer that we have done. We have insisted that people do that for the exams. So anyway, it is good practice for you to do it. Let me, however, show you a short code which goes back to our problem which we tried to solve by gradient descent and does it by the Gauss-Newton algorithm. So let's see that code now. So here is the problem. Once again, I have taken the same data set. Notice this thing of theta being a times 1 minus e to the power minus bt. Again, I am going to make the change from t to x and x to y, etc., etc. I'll make all those changes. I'll retain the a and b, same initial guesses. We saw that with gradient descent, it took a large number of guesses to get somewhere to convergence, and even then it turned out that the final answer was not physical, though I didn't show you why it is not physical. But our aim remains the same, to find out the optimal coefficients. We are going to start in the same way. You can see that I have input the same t and theta. I have done the same thing of x being t and y being theta. And up until here is just a equal to 35, b equal to 0.004. And I am just taking 5 iterations, which I have called epochs here. Now let's come to the derivative. Again, you would have seen the same expression within gradient descent 2. Notice y is a times 1 minus e to the power minus bx. dy dA, which we also calculated before, so I didn't do it once again in the previous video, is simply 1 minus e to the power minus bx. And dy dB is, I told you to be cautious here, a times x times e to the power minus bx. So till that time is the same. I have called it the gradient descent step. Really speaking, I should say that iterations start here. Okay. So this is our initial guess. And we calculate the gradients after the step has started. You should not get confused by the t here. I could probably call this I. As actually, let me retain the t just so as to not confuse the program right now. Okay, so y is calculated, dy dA is calculated, and dy dB is calculated, and I have just used that to calculate z. Okay, so let's just run it so that you have an intuition for what z looks like. Okay, so you come here and I take a step. Now, what is the size of z? Notice dy dA is a vector of size 6. It's all at every single point, at every single t point. Okay, so the point at time, you actually calculate whatever y is. Okay, so whatever dy dA is. Similarly for dy dB. Okay, so you calculate all of them. Now you put them together, and that's when you have z. Z is now, you can see, a 6 cross 2 vector. Why 6? 6 is the number of data points we took in time, and 2 is the number of a and b, the number of parameters that we have. So the derivative of how y hat, our prediction, changes with the first variable, and how y hat changes with the second variable. That's basically what we are trying to guess in z. The analogy is the design vector, as I told you, 1 and x. So this is what is known as the feature vector here. Now we calculate the left-hand side of this matrix. Okay, so notice the matrix we are solving, Z transpose Z delta A is Z transpose D. If you wish, we can call this minus Z transpose R. But I will stick with the D because that's the way I have programmed it. So I'll change the negative sign back. Okay, so nothing, minus of R is simply D. So you can see that here the left hand side is simply Z transpose Z. The right hand side is Z transpose multiplied by D. D is Y minus YH. I did not specify it separately. When you write a program in Excel, or if you do it by hand, you will have to actually calculate each one of these differences separately. What is Y and what is Y hat? You can see the value of Y and the value of Y hat are vastly different. So you can see that within this screen itself. So now here we solve for delta A. Again, what I am doing is the same as solving inverse of the left-hand side multiplied by the right-hand side, as I told you during the normal equations case also, is the same thing. So now once we do that, we actually have, let me just take a quick step. You have a solution. Now notice, since the left-hand side is now a 2 cross 2 matrix, right-hand side is simply a 2 cross 1 vector because it's the difference pre-multiplied by z prime. Now z prime has the right size to reduce this just to a 2 cross 1. So really speaking, we are only solving a 2 cross 2 system each time. Again, I highly recommend you do this by hand, both for the sake of exam and for the sake of your own understanding. So now you calculate a new A and you calculate a new B. Okay. This actually turns out to be much more stable. And I ran this for 5 epochs. And only the final value is displayed for some reason. I'll just rerun this again. That's because of the breakpoint. Let me run this again. So you can now see at the bottom, there is some amount of convergence, and this is actually a physical value. So the value of B, which has a time constant, actually needs to be, which we derived, if you might remember, it actually needs to be fairly small for this problem based on how we did it. If you wish, we can run this for a few more epochs. Let's say I run this for 10 epochs or 10 iterations. And you can see that it has more or less converged. See the last final 2 iterations, you can see both the A variable as well as the B variable have actually converged, just like with the usual Newton methods, and these turn out to be physical too. So this actually converges just within 10 iterations. Of course, each iteration is slightly painful, but this is far better than gradient descent. So this is the major advantage of the Gauss-Newton algorithm, and it's a powerful algorithm for nonlinear regression. Typically, almost all practical nonlinear regressions are done on some variant of this. What these variants are, we will discuss next week, because even Gauss-Newton has some problems with stability, and this is connected to the ill conditioning problem which I had discussed with you in the first week. So what we will see next week is some minor modifications of the Gauss-Newton algorithm and several other algorithms that we have seen so far in the course. So thank you. I hope to see you in the next week. Thanks.